The mountain didn't warn them. On a calm July evening in 1958, 3 fishing boats anchored in what they believed was safe harbor. The water was still. The sun hung low over Alaska. Everything seemed peaceful. Then in less than 4 minutes, 90 million tons of rock fell from the sky. The wave that followed climbed higher than the Empire State Building. It stripped forests from mountainsides at elevations where no wave should exist. It lifted boats over the tops of 100-foot trees. And when it was over, 2 boats had vanished entirely. And the survivors could barely describe what they'd witnessed, because what they saw defied everything science understood about water. 1,720 feet. That's how high the water climbed. Higher than any wave ever recorded in human history. Higher than should be physically possible. How does water defy gravity? How does a mountain fall silently? And why didn't anyone see it coming? This is the story of the Lituya Bay megatsunami, the night nature rewrote the rules. And 3 ordinary people found themselves facing a force that turned their world vertical. If stories like this, where science meets the raw power of our planet, fascinate you, this is your channel. Here on Fury of the Earth, we explore the moments when nature reminds us who's really in charge. Subscribe now and turn on notifications, because the forces that shaped this story are still active today. And the next chapter might be unfolding right now somewhere on Earth while we speak. The sleeping giants of Lituya Bay in the summer of 1958. The world still believed it understood the limits of nature's fury. The atomic age had arrived, humanity had split the atom, and science seemed poised to tame even the most violent forces on Earth. Yet in a remote fjord, along the southeastern coast of Alaska, something ancient was stirring, a geological drama millions of years in the making. Written in stone and ice, waiting for its final, catastrophic act. Lituya Bay is not a place that welcomes visitors easily. Carved by glaciers during the Pleistocene epoch, this T-shaped inlet stretches 7 miles inland from the Gulf of Alaska, flanked by mountains that rise nearly a mile into the sky. The Tlingit people, who have known these waters for thousands of years, called it a place of power and danger. Their legends spoke of spirits that dwelled in the bay's depths, and they warned against venturing too far into its waters. Science would later reveal that their ancestral wisdom was rooted in geological truth. The bay sits at a crossroads of titanic forces. Here, the Pacific Plate grinds relentlessly against the North American Plate along the Fairweather Fault, one of the most active transform boundaries on the planet. This is not the gentle collision that builds mountains over eons. This is a violent, grinding shear where sections of the Earth's crust slide past each other horizontally, accumulating stress year after year, decade after decade, until something must give. The Fairweather Fault runs like a surgical scar through southeast Alaska, and Lituya Bay lies directly in its path. By 1958, geologists understood that Alaska was earthquake country. The region had experienced significant seismic events before tremors that rattled windows and cracked foundations. But what they did not fully comprehend was how a single moment of rupture in the right place could trigger a cascade of consequences that would rewrite the textbooks on what water could do to stone, ice, and forest. The Bay had witnessed similar events before, though no scientist had been present to document them. Tree ring studies and geological surveys would later reveal evidence of massive wave action in the past scars on the landscape that told of waters rising to impossible heights, stripping hillsides bare and rearranging the very architecture of the coastline. The summer of 1958 arrived, with the endless daylight of the Alaskan high season. Fishing boats plied the rich waters of the Gulf of Alaska, and a handful of vessels sought shelter in Lituya Bay's protected waters. Among them were 3 boats whose crews would become unwitting witnesses to one of the most extraordinary geophysical events ever observed by human eyes. They came seeking fish and safety from the open ocean. What they would experience instead was a demonstration of nature's power so extreme that when they told their story, many would struggle to believe it. The stage was set. Millions of years of tectonic pressure had accumulated along the Fairweather Fault, high above the bay's northeastern arm. A massive section of mountainside weakened by countless freeze-thaw cycles, undermined by the retreat of glaciers, and destabilized by persistent seismic tremors hung in precarious equilibrium. The inlet's unique geometry, its steep-walled fjord carved deep below sea level, would act as a perfect channel for amplifying whatever force nature chose to unleash. And on the evening of July 9th, as the sun hung low over the Gulf of Alaska, casting long shadows across the water, every element of this geological equation was finally ready to resolve itself in a single, world-changing moment. The gathering storm, the Pacific Northwest, in the late 1950s was a frontier where human ambition met geological reality on terms nature had set millions of years before. Alaska had achieved statehood just months earlier, in January 1959, but on that July evening in 1958, it was still a territory wild, vast, and largely unmapped. The men who fished these waters were a particular breed, self-reliant, intimate with danger, and accustomed to reading the moods of sea and sky with the attention their lives demanded. 3 boats had anchored in Lituya Bay that evening. The Badger, captained by Bill Swanson with his wife Vivian aboard. The Eddery, piloted by Howard Ulrich and his 7-year-old son Junior. And the Sunmore, where Orville and Mickey Wagner prepared for what they thought would be a peaceful night at anchor. These were not tourists or adventurers seeking thrills. They were working people, fishing boats seeking shelter from the unpredictable Gulf of Alaska. Following a practice as old as maritime navigation, itself finding protected water when the ocean grew hostile. The day had been unremarkable. The kind of long, luminous Alaskan summer day where the sun barely dips below the horizon, painting the sky in shades of amber and rose that last for hours. The boats had anchored in different parts of the bay, each captain choosing his spot according to his own judgment and experience. The water was calm. The air was still. There was no reason to suspect that anything was wrong. No tremor or strange behavior from the wildlife that might have served as warning. Nature, it seemed, was keeping her own counsel. But beneath the surface, beneath the deceptive calm of that July evening, the Fairweather Fault was approaching its breaking point. For decades, perhaps centuries, stress had been accumulating along this transformed boundary. The Pacific Plate, driven by forces originating deep within the Earth's mantle, was attempting to slide northwest past the North American plate, but friction held the two masses locked together, preventing movement, storing energy like a compressed spring. This is the fundamental paradox of plate boundaries. They must move. Yet they resist moving, and the longer the resistance lasts, the more catastrophic the eventual release becomes. Geologists now understand that the Fairweather Fault is capable of producing earthquakes of magnitude 7.0 or greater. In 1958, the science of plate tectonics was still in its infancy. The theory would not gain widespread acceptance until the 1960s. The men anchored in Lituya Bay that night knew nothing of subduction zones or transform boundaries. They knew only that Alaska was earthquake country, that tremors were common, and that the mountains around them were young, still rising, still being shaped by forces they could feel but not name at approximately 10:15 p.m. local time. Those forces reached their threshold. Deep beneath the Fairweather Range, at a depth of several miles, rock that had been locked under unimaginable pressure suddenly failed. The fault ruptured. In an instant, sections of the Earth's crust that had been straining against each other for years lurched into motion. The Pacific Plate jumping as much as 21 feet horizontally and 3.5 feet vertically in a single, violent displacement. The earthquake that resulted measured 7.8 on the Richter scale, one of the most powerful seismic events recorded in North America during the 20th century. The energy released was equivalent to hundreds of atomic bombs. Seismic waves radiated outward from the hypocenter, traveling through bedrock at speeds of several miles per second. In Juneau, 120 miles to the southeast, buildings swayed and windows shattered. In Yakutat, 60 miles to the northwest, witnesses reported the ground rolling in visible waves. But the most dramatic effects were reserved for the epicenter itself, for the steep mountains surrounding Lituya Bay, and for the 3 small boats anchored in what they had believed was safe harbor. The shaking lasted less than a minute, but in that minute the landscape was fundamentally altered. Later investigations would reveal that the fault rupture extended for more than 180 miles along the Fairweather Fault system. Glaciers cracked and calved massive ice blocks. Mountainsides, already weakened by erosion and previous seismic activity, began to fail. And high above the northeastern arm of Lituya Bay, On the slopes of the ridge separating the inlet from Lituya Glacier, approximately 40 million cubic yards of rock loosened by the violent shaking, free from the friction that had held it in place, began to move 40 million cubic yards. To put that in perspective, it is roughly equivalent to 30 million cubic meters of material, enough to fill a cube nearly 1,000 feet on each side. This was not a minor rockfall or a simple avalanche. This was a significant portion of a mountain, surrendering to gravity in a single, apocalyptic collapse. The mountain falls. What happens when a mountain decides to move? The question seems almost philosophical until you witness the answer written in stone, water, and shattered forest. At 10:15 p.m. on July 9, 1958, the Fairweather earthquake provided that answer with a clarity that would forever change our understanding of what the Earth can do. The rockslide that followed the earthquake was not a consequence, it was a culmination. For years, perhaps decades, the northeastern face of the ridge above Lituya Bay had been in a state of slow, imperceptible failure. Glacial retreat had removed supporting ice. Freeze-thaw cycles had worked water into every crack and fissure, expanding and contracting, gradually prying the rock apart. Previous earthquakes had loosened the structure further, creating internal fractures invisible to any observer standing below. The mountain had been preparing to fall. The earthquake simply removed the last resistance. When the shaking began, the bonds holding that massive section of mountainside in place failed almost simultaneously along a broad front. 40 million cubic yards of rock, a mass estimated at roughly 90 million tons, separated from the mountain and began to accelerate downward under the influence of gravity. This was not a gentle sliding. This was freefall, a vertical drop of nearly 3,000 feet from the ridge into the waters of Gilbert Inlet at the head of Lituya Bay. To comprehend the energy involved, consider this: the rock slide struck the water traveling at an estimated 200 miles per hour. At that velocity, rock behaves less like solid matter and more like a fluid, a cascading avalanche that carries everything in its path. Trees centuries old were snapped like matchsticks. Ice from Lituya Glacier was sheared away and incorporated into the falling mass. The very bedrock of the slope was scoured clean, leaving exposed surfaces that would later be studied by geologists trying to piece together exactly what had occurred in those few seconds of violent transformation. The impact, when it came, released energy equivalent to several megatons of TNT, comparable to a small nuclear explosion. But unlike a bomb, which releases its energy as heat and radiation, this energy was transferred directly into the water of Gilbert Inlet. The laws of physics that govern such transfers are straightforward. Energy cannot be destroyed, only transformed. The kinetic energy of 90 million tons of falling rock had to go somewhere. It went into the water. The initial displacement was almost incomprehensible. The rockslide didn't simply splash into the bay, it obliterated the water that occupied that space, forcing it outward and upward with explosive violence. Geologists would later estimate that the impact created a wave that reached 1,720 feet up the opposite mountainside, higher than the Empire State Building, higher than any wave previously documented in human history. This was not a tsunami in the traditional sense, generated by undersea earthquakes displacing ocean floors. This was an impact-generated megatsunami, a phenomenon so rare that only a handful have ever been witnessed and survived. The physics of what happened next involves principles that seem to defy common sense. Water we think of as fluid, yielding soft. But water in sufficient quantity, moving with sufficient velocity, becomes a force that can pulverize granite. The wave that radiated outward from the impact site carried millions of tons of water, rock, ice, and shattered timber. It moved with a speed determined by the depth and geometry of the bay, estimated at between 100 and 130 miles per hour in the deeper sections. As the wave traveled down Gilbert Inlet toward the main body of Lituya Bay, it encountered the narrow entrance where the inlet joined the larger basin. Here, the topography of the bay created a focusing effect. The wave's energy, constrained by the steep walls of the fjord, was concentrated and amplified. On both sides of the inlet, the water surged up the mountainsides, stripping away everything in its path up to elevations of 500 to 600 feet. Centuries-old spruce forests were reduced to bare rock. Soil that had taken millennia to accumulate was scoured away in seconds. The trim line, the boundary between devastated slopes and untouched forest, would remain visible for decades. A stark horizontal line marking the exact height the water reached. The three boats anchored in the bay had, perhaps 1 minute's warning between the earthquake and the arrival of the wave. 1 minute to comprehend that the world had changed. That the laws they thought governed the behavior of water and mountains had been suspended. That survival would depend on reactions measured in seconds and decisions made with incomplete information under conditions of absolute terror. The Badger was anchored nearest to the head of the bay. The Sunmore was in the middle section. The Ettery was closest to the entrance near Cenotaph Island, where captains traditionally anchored for the night. What they saw approaching them was something beyond the vocabulary of seamanship. Not a wave in any conventional sense, not a swell that could be ridden out or a storm surge that could be weathered. This was a wall of water carrying the weight of a mountain, advancing with the inevitability of an avalanche and the speed of a freight train. Behind it, the entire head of the bay had been transformed. Where there had been water and ice and forest, there was now only churning chaos. A maelstrom of destruction still spreading, still reaching, still hungry. Moments of terror. Howard Ulrich was the first to see it. Standing on the deck of the Ettery with his 7-year-old son Junior beside him, he had just endured the most violent earthquake of his life. The boat had pitched and rolled at anchor, the water beneath them heaving as if the bay itself were alive. The sound of the quake had been overwhelming, a deep, grinding roar that seemed to come from everywhere at once. From the mountains, from the water, from the very air. And then, as the shaking subsided, he looked toward the head of the bay and saw something that his mind initially refused to accept as real. The entire mountainside was in motion. In the fading Arctic twilight, he could see the slope collapsing. Could see, or thought he could see, the tremendous splash as the rock hit the water. And then, surging toward him with impossible speed, came the wave. Later, when investigators asked him to describe what he saw, Ulrich would struggle for adequate words. It was not like any wave he had encountered in decades of fishing Alaskan waters. It was a wall, he said. A wall of water that filled the entire width of the inlet, pushing before it a churning mass of ice, timber, and debris. The wave was not uniform. Its leading edge rose and fell as it traveled, responding to the contours of the bay bottom. But its overall height as it bore down on the anchored boats was estimated at between 50 and 100 feet, a moving mountain of water in a channel barely a mile wide. The sound it made was like continuous thunder, a roar that drowned out thought, that made communication impossible, that reduced the world to pure primal sensation, fear, adrenaline, the desperate animal need to survive. Ulrich made a decision that saved his life and his son's. Rather than attempt to raise anchor a process that would take precious seconds he did not have, he grabbed an axe and cut the anchor line. The Ettery, freed from its mooring, was carried up by the wave as it arrived. Not gently, not like a boat riding a swell. The vessel was lifted bodily, wrenched upward by forces that stressed every timber and rivet, that turned the fishing boat into a piece of driftwood in a cataract. Ulrich gunned the engine, fighting to keep the bow pointed into the wave. Knowing that if the boat turned broadside it would capsize and they would be lost, the Ettery rode up the face of the wave, climbing what felt like a vertical wall of water. At the crest, Ulrich could see over the tops of trees on the shore trees that were themselves 80 to 100 feet tall. The boat hung there for a moment that seemed to stretch into eternity, balanced between sea and sky, between life and death. And then it descended the back of the wave, plunging down into the trough with a violence that should have torn the vessel apart. Somehow the Ettery held together. Somehow Howard Ulrich maintained enough control to keep the boat oriented correctly as successive waves, smaller than the first, but still massive by any normal standard, continued to surge through the bay. The boat was carried toward the entrance of Lituya Bay, swept along by currents that made navigation meaningless, that reduced seamanship to pure survival instinct. They were, for those minutes, not in control of their fate. They were passengers on a journey the ocean had chosen for them. Bill and Vivian Swanson, aboard the Badger, were not as fortunate in their positioning. Their boat was anchored closer to the head of the bay, nearer to the source of the destruction. They too saw the wave coming. They too made the decision to cut their anchor line, but the Badger was caught more directly by the initial surge. The boat was lifted higher than the Etrury had. Ben Swanson would later estimate that they rose at least 80 feet and was carried with terrifying speed toward the southern shore of the bay. The Badger struck the trees at the wave's crest. The impact was catastrophic. The boat smashed through the forest canopy, breaking apart as it collided with trees that had stood for centuries. Bill Swanson was thrown clear into the water. His wife Vivian disappeared into the maelstrom. When the water finally receded, when the chaos finally began to settle, Swanson found himself alone in the frigid water, clinging to debris, surrounded by the wreckage of his boat and his life. He would be rescued hours later by another fishing vessel, one of the few survivors of the night. Vivian Swanson's body was never recovered. Orville and Mickey Wagner aboard the Sunmore had no chance at all. Their boat was positioned in the middle section of the bay, directly in the path of the wave as it surged down the inlet. Witnesses including Ulrich from the Etrury reported seeing the Sunmore lifted by the wave, but the boat apparently capsized in the turbulence. Neither Orville nor Mickey Wagner survived. Like Vivian Swanson, their bodies were never found. The Sunmore itself vanished, broken into pieces too small to identify, scattered across miles of devastated coastline, or dragged out to sea by the powerful currents that followed the wave's passage. In less than 5 minutes. The wave had traveled the length of Lituya Bay, had claimed 2 lives, had destroyed 2 boats and severely damaged a third, and had rewritten the landscape on a scale that would have taken centuries of normal erosion to accomplish. The survivors, Howard Ulrich, his son Jr., and Bill Swanson, would carry the memory of those minutes for the rest of their lives, would wake from nightmares in which mountains fell and water rose beyond reason, in which the world revealed its capacity for sudden, absolute violence. The science of the impossible in the days and weeks following the Lituya Bay event, as news of the megatsunami spread through scientific circles. The initial reaction was profound skepticism. The survivors' accounts seemed physically impossible. A wave 1,720 feet high, water climbing mountainsides to elevations that exceeded the height of the tallest skyscrapers. These claims defied everything geologists and oceanographers thought they understood about water dynamics and wave mechanics. But the evidence was undeniable. When research teams finally reached Lituya Bay in the weeks following the disaster, they found a landscape that told an unambiguous story. The trim line, the boundary between destroyed forest and intact vegetation, ran horizontally across both sides of Gilbert Inlet at a maximum elevation of 1,720 feet above sea level. Below that line, everything was gone. Ancient spruce trees had been snapped off at their bases or uprooted entirely. Soil had been scoured down to bedrock. In some places, the rock itself showed fresh scarring from the passage of debris-laden water moving at velocities that allowed ice and timber to act as battering rams. The geologist, Don Miller, working for the United States Geological Survey, led the initial scientific investigation. Miller was uniquely qualified for the task. He had been studying Lituya Bay for years and had actually predicted that the area was at risk for exactly this type of event, though even he had not imagined the scale of what would eventually occur. His surveys revealed details that would prove crucial to understanding the mechanics of what had happened. The rockslide source area was clearly visible on the northeastern slope. Approximately 40 million cubic yards of material had detached from the mountain, a volume large enough to bury Manhattan to a depth of 30 feet. The slide had originated from an elevation of about 3,000 feet and had fallen nearly vertically into Gilbert Inlet, which at that point was approximately 220 feet deep. The geometry of this impact, massive volume, extreme vertical drop, confined water body created the perfect conditions for generating a displacement wave of unprecedented magnitude. Miller's team also discovered something remarkable about Lituya Bay's history. This was not the first time such an event had occurred. Tree ring analysis from the surrounding forests revealed evidence of at least 3 previous giant waves within the past 150 years in 1936, 1899, and 1874. Each had stripped the hillsides to different elevations, creating distinct bands of forest regrowth that could be read like pages in a history book. The 1936 event had reached approximately 490 feet. The 1899 wave had climbed to about 200 feet. But the 1958 event dwarfed them all. The question that consumed scientists was, how? How could water reach such extreme heights? The answer lay in a combination of factors, each amplifying the others in a cascade of consequences that transformed an already enormous rockslide into something truly apocalyptic. First, there was the sheer volume and velocity of the rockslide impact. 90 million tons of rock, traveling at approximately 200 miles per hour, striking water in a confined space, creates what physicists call a splash wave or impact. Tsunami. The initial displacement of water was almost instantaneous. The rock essentially occupying space that water had occupied a fraction of a second before, forcing that water to go somewhere. The only direction available was up and outward. Second, the geometry of Gilbert Inlet acted as a focusing mechanism. The inlet is narrow, less than half a mile wide at the point of impact, and steep-walled. When the initial splash occurred, water surged up the opposite mountainside, not just from the direct impact, but because there was literally nowhere else for it to go. The 1,720-foot run-up on the opposite slope was not the height of the wave itself, but rather the result of water being channeled and compressed by the topography, forced upward by its own momentum and the confined space. Third, the wave that traveled down the bay toward the anchored boats was a different phenomenon from the initial splash. This was what scientists call a bore, a wall of water that maintains its form because it is moving in a confined channel. Unlike ocean waves, which are primarily surface phenomena with energy dissipating rapidly with depth, the bore in Lituya Bay involved the entire water column from surface to bottom, pushing forward like a moving dam. The physics of such waves was not well understood in 1958. Indeed, the Lituya Bay event would prove to be a crucial data point in developing models of impact-generated megatsunamis. Scientists realized that previous theoretical limits on wave height had been based on assumptions. That did not account for the extreme conditions that could occur in confined bodies of water with the right topography. Subsequent research, including laboratory experiments and computer modeling, has confirmed the basic mechanisms that Miller proposed. Scale models of Lituya Bay, subjected to simulated rockslides, have reproduced similar wave patterns. Computer simulations using modern fluid dynamics software have validated the survivors' accounts and the physical evidence. What seemed impossible in 1958 is now understood as an inevitable consequence of known physical laws operating under extreme conditions. The Lituya Bay megatsunami remains the highest wave ever documented in modern history. It exceeded by a factor of 4 the previous recorded tsunami in Ishigaki, Japan in 1771 that reached approximately 280 feet. It was more than 3 times the height of the devastating 2004 Indian Ocean tsunami, which at its maximum measured around 100 feet. The only comparable events in geological history are theoretical impact tsunamis from asteroid strikes or massive volcanic collapses, catastrophes that occur on timescales measured in millions of years. Echoes in deep time. The Lituya Bay event, for all its violence and spectacle, was not an anomaly. It was a reminder, a visceral demonstration that the Earth operates on principles and timescales that dwarf human experience. To understand the true significance of what happened on that July evening in 1958, we must step back from the immediate drama and consider the deeper context. The geological forces that make such events not just possible, but inevitable. The Pacific Ring of Fire, that vast arc of volcanic and seismic activity encircling the Pacific Ocean, is the most geologically active region on Earth. It is here that tectonic plates collide, subduct, and grind past one another, releasing energy that has been accumulating for decades or centuries in sudden, catastrophic bursts. Alaska sits at the northern apex of this ring, where the Pacific Plate meets the North American Plate along multiple fault systems. The Fairweather Fault, scene of the 1958 earthquake, is just one thread in a complex web of fractures that mark the boundary between these continental scale masses of rock. Transform faults like the Fairweather are fundamentally different from the subduction zones that generate the largest earthquakes and tsunamis. instead of one plate diving beneath another. Transform boundaries involve horizontal sliding, the kind of motion visible at the San Andreas Fault in California, another member of the same geological family. But horizontal motion does not mean less dangerous. The friction between plates can lock them together for years, allowing stress to build until the rock finally fails. When it does, the sudden release of energy can be devastating. The 1958 earthquake was powerful, magnitude 7.8, but not unprecedented. Alaska has experienced larger quakes, including the magnitude 9.2 Good Friday earthquake of 1964, which remains the second largest earthquake ever recorded by instruments. What made the Lituya Bay event exceptional was not the earthquake itself, but the secondary consequences, the rock slide, and the unique geography that transformed kinetic energy into hydraulic catastrophe. Rock slides and landslides are common in tectonically active mountain regions. Alaska's coastal ranges are young mountains, still rising, still being shaped by ongoing tectonic forces. Glaciers have carved deep valleys and left mountainsides oversteepened and unstable. When glaciers retreat, as they have been doing throughout Alaska for more than a century, they remove the supporting buttress that held unstable slopes in place. The rock, weakened by millions of freeze-thaw cycles, riddled with fractures from previous earthquakes, sits in a state of precarious equilibrium, waiting for the trigger that will send it cascading downward. That trigger can be an earthquake, as it was in 1958. It can be heavy rainfall that adds weight and lubricates internal fracture planes. It can be glacial melting that undermines the base of a slope. Or it can be nothing dramatic at all, just the slow, patient work of gravity over years and decades until one day, without warning, the balance tips and the mountain moves. Geologists call these threshold phenomena systems that can absorb stress up to a certain point, then fail suddenly and completely. The 1958 event was not even the largest rockslide-generated wave on record. That distinction may belong to a prehistoric event in Spirit Lake, Washington, where geological evidence suggests a landslide created a wave that reached 850 feet before being exceeded by the Lituya Bay wave. And in 1963, just 5 years after Lituya Bay, a massive landslide into the Vajont Dam reservoir in Italy generated a wave that overtopped the dam at 820 feet, killing nearly 2,000 people in the valley below. The Vajont disaster proved that Lituya Bay was not a unique occurrence, but rather an example of a class of hazards that remained poorly understood and inadequately anticipated. More recently, geological surveys have identified evidence of ancient megatsunamis that make even Lituya Bay seem modest. On the flanks of volcanic islands in Hawaii, researchers have found deposits of coral and marine sediments at elevations exceeding 1,000 feet, carried there by waves generated when massive sections of the volcanic islands collapsed into the ocean. These events, occurring perhaps once every 100,000 years, would have generated open ocean tsunamis hundreds of feet high, capable of devastating coastlines thousands of miles away. In Norway, geologists have studied the Storegga slide, a submarine landslide that occurred approximately 8,200 years ago. An estimated 800 cubic miles of sediment, thousands of times larger than the Lituya Bay rockslide, collapsed off the continental shelf, generating a tsunami that struck the coasts of Scotland, Norway, and Greenland with waves up to 80 feet high. Evidence of this event has been found in sediment cores from coastal areas, preserving a snapshot of a catastrophe that occurred when human civilization was still in its infancy. These deep-time perspectives reveal a troubling truth. The Earth is capable of generating waves and floods on scales that exceed anything in recorded human history. The 1958 Lituya Bay event happened to occur in a remote location where only a handful of people witnessed it. The 1964 Good Friday earthquake generated a tsunami that killed 139 people across Alaska, British Columbia, and as far south as California. The 2004 Indian Ocean tsunami killed an estimated 230,000 people across 14 countries. Each event reminds us that our coastal cities, our maritime infrastructure, our assumptions about where it is safe to build and live, are all based on the relatively benign geological conditions of the past few centuries. But the geological record tells us that this recent past is not necessarily representative of what the Earth can do. The question is not whether another megatsunami will occur. The physics and geology guarantee that it will. The question is where, when, and whether we will be prepared when it does. The human element in the aftermath of the Lituya Bay disaster. As scientists worked to understand the physical mechanics of what had occurred, another set of questions emerged, questions about human perception, decision-making, and the psychological impact of witnessing an event that challenged fundamental assumptions about the world. The survivors, Howard Ulrich, his young son Jr., and Bill Swanson, had experienced something that few people in history could claim. They had seen nature operate at a scale that exceeded the bounds of normal human experience, and they had lived to tell about it. Howard Ulrich's testimony became crucial to the scientific investigation. His account was detailed, precise, and consistent across multiple interviews. He described not just what he saw, but what he felt, the quality of the sound, the way the boat responded, the speed at which events unfolded. His estimate that the Estuary had risen to a height where he could see over 80-foot trees was initially dismissed by some investigators as exaggeration born of trauma. But when those estimates were compared with the physical evidence, the trim lines, the distribution of debris, the damage patterns, they proved remarkably accurate. Ulrich's decision to cut the anchor line, rather than attempt to raise it conventionally, was made in seconds, under conditions of extreme stress, with incomplete information. It was, by any objective measure, the right decision, the decision that saved his life and his son's. But it was not obvious. Cutting an anchor line means losing expensive equipment. It means setting your vessel adrift in conditions that are already dangerous. For a commercial fisherman, for whom the boat represents livelihood and life savings, the psychological barrier to deliberately cutting yourself free from your mooring is substantial. Yet, Ulrich made that choice without hesitation. When asked later how he knew what to do, he struggled to articulate a clear reasoning process. It was instinct, he said. A lifetime of reading water and weather. An understanding that when the world changes fundamentally, old rules no longer apply. He saw the wave coming, recognized that it was beyond anything he had encountered before, and acted on the principle that being mobile, even uncontrolled, was preferable to being anchored in place. Bill Swanson's experience was darker, marked by loss and the randomness of survival. Why was he thrown clear of the Badger when it struck the trees, while his wife Vivian was not? Why did he find debris to cling to, while Orville and Mickey Wagner disappeared entirely? These questions have no satisfying answers. Survival in catastrophic events often comes down to factors, measured in inches and fractions of seconds, variables so small that they appear, from any human perspective, to be pure chance. Swanson spent hours in the water before being rescued. The temperature of Alaskan waters in July hovers around 50 degrees Fahrenheit, cold enough to cause hypothermia within an hour or two. That he survived the cold, the exhaustion, the physical trauma of the boat's destruction, and the psychological shock of losing his wife speaks to both physical resilience and sheer luck. In his later interviews, Swanson spoke very little about the technical details of the wave. He spoke instead about loss, about the seconds before impact when he and Vivian were together, and about the hollow silence that followed when he found himself alone. The deaths of Vivian Swanson, Orville Wagner, and Mickey Wagner were recorded as drownings, though the actual cause was almost certainly more complex trauma from impact with the boat or debris. Hypothermia, or simply being overwhelmed by forces against which human strength was meaningless. Their bodies were never recovered, likely carried out to sea by the powerful currents that followed the wave's passage through the bay, or buried under tons of sediment and debris that settled in the aftermath. For the Tlingit people, whose ancestors had known Lituya Bay for thousands of years, the 1958 event was confirmation of what their oral traditions had always maintained, that the bay was a place of power and danger, that the spirits dwelling there were not to be trifled with, that prudent people treated these waters with respect and caution. Western science, in its investigation of the event, essentially validated these traditional warnings, translating them from the language of myth into the language of seismology and fluid dynamics. The wisdom was the same. Only the vocabulary had changed. The psychological impact on the survivors was profound and lasting. Howard Ulrich continued to fish Alaskan waters, but he never again anchored in Lituya Bay. The memory of that night, the sound of the mountain falling, the sight of the wave bearing down on him, the sensation of being lifted bodily by water that should not have been able to behave as it did remained vivid for the rest of his life. In interviews conducted decades later, his voice would still tighten when describing those moments, his hands moving unconsciously to illustrate the angle of the boat, the height of the wave, the impossible geometry of water climbing mountainsides. Junior Ulrich, who was 7 years old on the night of the tsunami, grew up with the distinction of being one of the youngest survivors of a megatsunami in recorded history. The experience shaped his understanding of nature's power in ways that are difficult to quantify. There is a difference between knowing intellectually that the Earth is dynamic and dangerous, and experiencing that truth directly at an age when the brain is still forming its fundamental models of how the world works. Bill Swanson eventually returned to fishing, though friends noted that he was changed by the experience, more withdrawn, carrying a grief that never fully resolved. The question that haunted him, why he survived when Vivian did not, has no answer that provides comfort. Catastrophes do not follow moral logic. They do not spare the deserving or punish the guilty. They simply happen indifferent to human hopes, fears, and ideas about fairness, vigilance, and vulnerability. The Lituya Bay megatsunami of 1958 marked a watershed in the scientific understanding of impact-generated waves. But it also exposed a troubling reality. Despite our advances in monitoring technology and geological knowledge, our ability to predict such events remains fundamentally limited. The earthquake that triggered the rockslide could be measured and located by seismographs scattered across Alaska and the Pacific Rim, but the rockslide itself, the critical secondary event that transformed a large earthquake into a historic catastrophe, occurred with no advance warning whatsoever. This limitation persists today. More than 6 decades later, we have built increasingly sophisticated systems for detecting earthquakes, monitoring volcanic activity, and tracking ocean-generated tsunamis. The Pacific Tsunami Warning Center, established in 1949 after a devastating tsunami struck Hawaii, now coordinates a network of sensors and buoys across the Pacific Ocean. These systems can detect the pressure waves generated by undersea earthquakes and provide warnings to coastal communities hours before tsunami waves arrive. But impact-generated megatsunami waves created by rockslides, landslides, or volcanic collapses into bodies of water operate on different timescales and present different challenges. The warning time for an impact tsunami is measured in minutes or seconds, not hours. The wave is generated locally, travels quickly through confined waters, and strikes before any warning can be issued or evacuation initiated. In Lituya Bay, the time between the earthquake and the wave's arrival at the anchored boats was perhaps 60 seconds. Even if a perfect detection system had been in place, even if an alarm had sounded the instant the rockslide began, there would have been no time for the crews to do anything differently than what they did. This uncomfortable truth applies to numerous other locations around the world where similar conditions exist. The Norwegian coastline, with its deep fjords and steep mountains, presents similar hazards. In 1934, a rockslide into the fjord in Norway generated a wave that killed 40 people. Geological surveys have identified numerous other locations where unstable slopes overhang water-filled valleys, potential Lituya bays waiting for their triggering earthquake or critical threshold of instability. The industry of reservoir construction adds another dimension to the risk. The Vajont Dam disaster in Italy in 1963 demonstrated that human engineering can inadvertently create the conditions for catastrophic impact waves. When the reservoir behind the Vajont Dam was filled, the water infiltrated the porous rock of the surrounding mountainside, adding weight and reducing friction along internal fracture planes. On October 9, 1963, approximately 260 million cubic meters of rock, more than 6 times the volume of the Lituya Bay rockslide, detached from Montauk and slid into the reservoir. The wave generated by the Vajont rockslide overtopped the dam by more than 800 feet and swept into the valley below, destroying several villages and killing an estimated 1,900 to 2,500 people. The dam itself, remarkably, remained structurally intact, a testament to Italian engineering and a grim irony. The structure survived. The people as built to serve did not. Investigations revealed that geologists had warned about the instability of the slope before the reservoir was filled, but those warnings had been inadequately heeded. The disaster became a case study in the importance of geological assessment and the catastrophic consequences of ignoring expert warnings. Modern monitoring has improved, but not eliminated, the risk. In Alaska, the United States Geological Survey maintains a network of seismometers and GPS stations that track ground deformation and seismic activity. After significant earthquakes, rapid assessment teams can be deployed to evaluate secondary hazards, including potential landslides. But these are reactive measures, responses to events that have already begun. The fundamental challenge predicting exactly when an unstable slope will fail remains largely unsolved. Some progress has been made through remote sensing technology. Satellite-based radar interferometry can detect millimeter-scale movements of the ground surface, potentially identifying slopes that are creeping toward failure. In Norway, such systems now monitor known unstable areas, including the Kaikans rock slide, a slowly moving mass of rock above a fjord that threatens to generate a tsunami if it collapses suddenly. The monitoring provides data, but not certainty. The slope has been moving slowly for years. It could fail tomorrow, or it could remain stable for decades. The decision of whether to evacuate nearby communities, and when, involves balancing potential risk against the very real costs and disruptions of relocation. Climate change adds a new variable to these ancient hazards. As temperatures rise, mountain glaciers continue their retreat, a process that has been accelerating for more than a century. The loss of ice removes support from valley walls and mountain slopes that have been buttressed by glaciers for thousands of years. Permafrost, permanently frozen ground that helps stabilize slopes in Arctic and alpine regions, is thawing, allowing water to penetrate deeper into fractures and reducing the friction that holds rock masses in place. Scientists have documented increased landslide and rockslide activity in alpine regions worldwide, correlating with rising temperatures and glacial retreat. Lituya Bay itself has changed since 1958. The glacier at the head of Gilbert Inlet has continued to retreat. The scar left by the rockslide remains visible, a massive excavation on the mountainside that will require centuries to weather and erode. The trim lines marking the wave's passage have gradually become less distinct as vegetation slowly reclaims the scoured slopes, but they remain detectable, a legacy written in the age structure of the forest. The bay continues to experience earthquakes, smaller ones, rarely noticed by anyone not actively monitoring seismic data, but reminders that the tectonic forces responsible for the 1958 event remain active. Could it happen again? The answer is unequivocally yes. The question is not whether another megatsunami will occur at Lituya Bay or somewhere similar, but when. The geological conditions that made the 1958 event possible, active faults, steep topography, confined water bodies, unstable slopes, exist in numerous locations worldwide. The triggering mechanism, an earthquake, a storm, a threshold of accumulated instability, will eventually occur. And when it does, the physics will be the same. The consequences potentially as catastrophic. The enduring questions. The landscape of Lituya Bay today bears silent witness to the events of July 9, 1958. The fjord remains remote, accessible primarily by boat or floatplane, visited mainly by adventurous kayakers and researchers who come to study what the Earth revealed in those few minutes of violence. The water is calm most days, reflecting the mountains that rise steeply on both sides. It is difficult, standing on those shores in the quiet of an Alaskan summer, to imagine the forces that once transformed this place into a cauldron of destruction. But the evidence remains. The trim line, though softened by decades of vegetation regrowth, still marks a horizontal boundary between old-growth forest and younger trees. Line etched at elevations that seem impossible until you understand the physics that placed it there. The rockslide scar on the northeastern slope is still visible, a lighter patch of exposed rock that has weathered differently than the surrounding stone. These are the permanent signatures of impermanent chaos, reminders that the Earth's surface, which seems so stable on human timescales, is in constant, violent flux when viewed across geological time. The scientific legacy of Lituya Bay extends far beyond the immediate documentation of the event. The megatsunami became a crucial data point in developing models of impact-generated waves, influencing everything from coastal hazard assessments to the design of dams and reservoirs. Computer simulations of the event, conducted decades later using advanced fluid dynamics software, have validated the eyewitness accounts and demonstrated that the extreme wave heights were not aberrations but inevitable consequences of the specific conditions present that night. These models have practical applications. Engineers designing reservoirs in mountainous terrain now routinely assess the landslide potential of surrounding slopes and model the wave consequences if a slope failure occurs. Coastal communities and fjord regions have incorporated impact tsunami scenarios into their hazard planning. The Norwegian government, recognizing the risks posed by unstable slopes above populated fjords, has invested in monitoring systems and developed evacuation plans based partly on lessons learned from Lituya Bay and Vagent. Yet for all our increased understanding, fundamental limitations remain. We can identify unstable slopes and quantify risk in probabilistic terms, but we cannot predict the exact moment when threshold conditions will be reached and failure will occur. We can model the waves that would result from a given rockslide, but we cannot prevent the rockslide from happening. We can issue warnings after an earthquake, but we cannot provide advance notice before an impact tsunami strikes a nearby shoreline. This tension between knowledge and capability defines much of our relationship with geological hazards. We know more about the Earth's behavior than at any point in human history. We can measure movements of tectonic plates to millimeter precision. We can monitor volcanic gas emissions and ground deformation in real time. We can reconstruct the history of ancient catastrophes from sediment layers and tree rings. Yet all this knowledge does not grant us control. It grants us only understanding and, perhaps, if we are wise, humility. The personal stories of the survivors have become part of the historical record, preserved in interview transcripts, documentary footage, and the reports compiled by investigators like Doan Miller. Howard Ulrich passed away in 2002, his son Junior in 2019, Bill Swanson lived until 1997, carrying until the end the memory of those seconds when his life changed irrevocably. Their testimonies remain valuable not just as historical documents, but as reminders that, behind every geological statistic, every magnitude number, every casualty count, every cubic meter of displaced rock are human experiences of fear, loss, survival, and grief. The Lituya Bay event also raises uncomfortable questions about risk and development. The bay was remote in 1958, home to no permanent settlements, visited only by fishing boats seeking temporary shelter. But many locations with similar geological conditions are not so isolated. Coastal cities sit at the heads of fjords in Norway, Chile, New Zealand, and Alaska itself. Reservoirs nestle in mountain valleys below slopes that show signs of instability. Millions of people live in areas where the combination of seismicity, steep topography, and water could, under the right circumstances, produce consequences similar to or exceeding what occurred at Lituya Bay. The economic and social costs of avoiding these risks entirely would be prohibitive. We cannot abandon every coastline, every mountain valley, every location where geological hazards exist. To do so would be to abandon much of the habitable Earth. Instead, we navigate a complex calculus of acceptable risk, informed by scientific understanding but ultimately involving value judgments about safety, economics, and the acceptable probability of catastrophic loss. Lituya Bay offers no comfortable lessons, no easy reassurances. It demonstrates that the Earth operates according to physical laws that are indifferent to human presence or preference. It shows that rare events occurring perhaps once per century or once per millennium in any given location can nevertheless be catastrophic when they do occur. It reminds us that our civilization, with all its technology, all its knowledge, all its apparent mastery over the natural world, remains fundamentally vulnerable to forces we can measure but not control. Perhaps the most profound lesson is simply this: the Earth is old, patient, and powerful in ways that exceed human scale. The mountains that seem eternal are young and still rising. The coastlines that appear stable are temporary arrangements, constantly being renegotiated between land and sea. The ground beneath our feet is moving, sometimes slowly, sometimes suddenly, always according to principles that operated long before. We were here to observe them and will continue long after we are gone. standing on the shore of Lituya Bay today. One can imagine, though perhaps not fully comprehend, what Howard Ulrich saw when he looked up the inlet on that. July evening in 1958. The mountain falling. The water rising. The fundamental rules of the world being suspended for a few terrible minutes, while nature demonstrated what it could do when the right conditions aligned. It happened once. It will happen again, somewhere, sometime. And all our knowledge, all our technology, all our carefully constructed models and monitoring systems will allow us only to measure and document, to understand and remember, but not to prevent or control. In the face of such forces, wisdom lies not in the illusion of mastery, but in respect, preparedness, and the recognition of our limits.